Good morning everyone. So this is the last section of the chapter recurrence relation, where we will see how can we solve a recurrence relation using generating function. So to begin with, let's see the problem. An is equal to 2an minus 1 plus 3an minus 2 with the initial conditions, and we need to solve it using generating function. So when I say the generating function, then I will assume the generating function is ordinary generating function, which is a naught plus a1x plus a n x raised to the power n, which is summation a n x raised to the power n. Yes, so if I have to use the generating function to solve the recurrence relation, and you can see there are terms like a n minus 1, so I must try to write the recurrence relation in terms of g of x. To do so, I must multiply the recurrence relation by x raised to the power n and take the summation. Since I have an minus 2, so therefore my summation must start from n is equal to 2. An minus 1 x raised to the power n, and the last one is 3 an minus 2 and x raised to the power n. Now if you see the first term, and if I want to transform it in terms of the g of x, then it has two terms missing, a naught and a1x. So I add a naught and a1x and subtract, so it becomes g of x minus a naught minus a1x. In the next term, I should take x outside and see how it looks like. So it is n to infinity an minus 1 x raised to the power n minus 1, and in the last term I will take x square outside and I write it like this. Now again, in this term, summation n from 2 to, so if you start from 2, so the first term is a1 x plus a2 x square and so on. So it means if I compare with g of x, then only missing term is a naught. So I can write g of x minus a naught plus 3x square, and if I see this summation, then it starts from a0, then a1x and so on. So it means it is simply g of x. Now I have given the value of a naught and a1, so I must substitute the given values. So this becomes g of x minus, my a naught is 2, a1 is 2, so g of x minus 2 minus 2x, then I have 2x, g of x minus 2, so 2x g of x minus 2, let me write it again, g of x minus 2 minus 2x, 2x g of x minus 2 plus 3x square and g of x. So now let's substitute the values. So if I take the g of x term on one side, it becomes 1 minus 2x minus 3x square, and the right hand side would be 2 and then minus 2x. So if I simplify it, then it becomes g of x is 2 1 minus x and divided by 1 minus 2x minus 3x square, which is same as x plus 1 and 3x minus 1. Now for the recurrence relation, recall that in the generating function we are looking for the coefficient of x raised to the power n, which is an. So we are looking for an. It means for this generating function I should find the coefficient of x raised to the power n. But in this form I cannot find, so I must use the partial fraction, and therefore this becomes 1 by x plus 1 plus 1 by 1 minus x. Now this is the binomial expansion, 1 minus x plus x square minus x cube and so on, which means the coefficient of x raised to the power n is minus 1 raised to the power n, and in the second one it becomes 1 plus 3x plus 3 square x square and so on, so which is 3 raised to the power n. So this is my required an, which is the solution of the recurrence relation using generating function. Let's try one more question. Again I will use the same approach. So multiply by x raised to the power n and taking the summation an minus 1 x raised to the power n plus summation n x raised to the power n is from 1 to infinity. Now the first term again a naught is missing, so this is g of x minus a naught. In the second term I take x outside, so it becomes an minus 1 xn minus 1, and in the last term even if I start summation from 0 nothing would change, because if I put n is equal to 0 it won't change anything. So this becomes g of x minus 1, this becomes x, and this is the first term is a naught, the next one is a1x, so I am not missing anything, but I do not know how to write it in the form of an polynomial or some expression. So to see it I have summation n x raised to the power n. Yes, now recall the initial generating function, the summation method. So initial generating function if I choose as this one, so if I differentiate 1 by 1 minus x, so the first term is 1 and so on, and there would be a term n xn minus 1, but I need n xn, so I multiply it by x. So x d by dx of 1 by 1 minus x, this would be so on, and n x raised to the power n and so on, which is summation n x raised to the power n. Either n starts from 0 or 1, doesn't matter, both are same. And the left hand side, which is d by dx of 1 minus x, which is 1 by 1 minus x whole square, and multiply by x. It means my original equation becomes g of x minus 1 x g of x plus x 1 minus x whole square, and that gives me g of x if I take on that side and divide by 1 minus x. So this is how it looks like. Now coefficient of x raised to the power n. So from the first term it is 1 only, because 1 plus x square and so on, and from the second term I need coefficient of x raised to the power n minus 1 in 1 minus x raised to the power minus 3, which is r plus n minus 1 r. So n minus 1 plus 3 minus 1, we have discussed it many times. So this becomes 1 plus c n plus 1. Instead of n minus 1 I can also write it as, just for the simplification. So this is my required a. Moving further, this is the last one, which says that now we are considering the two variables. So it says if g and x is a family of generating function which is given as follows, a and k, the recurrence relation is given as follows, a n 0, a n 1. So we need to find a and k. So find a functional relation among j and x and solve it to obtain a and k. So now first see, I have given g n x is summation a n comma k x raised to the power k, k from 0 to n, and the recurrence relation is a n k, a n minus 1 comma k plus a n minus 1 k minus 1. So multiplying by x raised to the power k and taking the summation, since n minus 1 is there I must start from 1 only. So starting from, let's write it like k from 1 to n, a n comma k x raised to the power k is a n minus 1 comma k and a n minus 1 comma k minus 1. and x raised to the power k is there. Now the first term is simply one term is missing, a when you start from k is equal to 0, so a n comma 0, which is equal to 1 using the initial condition. So this is j n x minus 1. If you see the second term, there I must take x outside and it becomes a n minus 1 comma k x raised to the power. Even in the second term I should not take x outside, and let's me do it on the next slide. So the second term is k is equal to 1 to n a n minus 1 comma k and x raised to the power k. So if you see it, then your first term is a n minus 1 1, a n minus 1 2, and so on, and the last term is a n minus 1 comma n, which is 0. So I have terms till a n minus 1 comma a n minus 1. So this is in the form of g n minus 1 minus the first term, which is 1, the initial condition. And the second term is a n minus 1 k minus 1 x raised to the power k. If I take x outside, it becomes a n minus 1 k n minus 1 and x raised to the power k minus 1. K is starting from 1. So the first term you will get is a n minus 1 0, a n minus 2 1, a n minus 1 then 1, a n minus 1 2. So it is simply so the last term simply becomes x and gn minus 1. So it means I have on the left hand side I have gn x minus 1, and on the right hand side I have the first term is gn minus 1 minus 1 and then x gn minus 1. So minus 1 would cancel out. So your gn x becomes 1 plus x gn minus 1, which is same as 1 plus x square gn minus 2, 1 plus x cube gn minus 3, and so on, 1 plus x raised to the power n g0. Yes, g0 is a 0 comma 0, which is 1 from the initial condition. It means gnx is 1 plus x raised to the power n, where the coefficient of x raised to the power k, which we are looking for a n k, is simply c n k, which is the required answer. So that's all from today's class. In the next class we will start inclusion exclusion principle.